Hello! So this is quite a tradition at conferences, right at the end to have sort of lightning talks, unorganised demonstrations and that type of thing. So if you've got an idea for one, start thinking about it. Meanwhile, I'm going to kick it off with a little bit of a demonstration of debugging using JTag. Now, what I've got here is a cube, and it's got this cable here which Philip assures me on pain of death that this cable is very, very strong, despite the fact that it looks about the most fragile cable you've ever seen in your life. But apparently it's made of unobtainium super strong stuff. And it comes out of the connector. You've got two debug connectors on the side of a cube, one for the I/O microcontroller, the other for the main FMU. There is an equivalent on a PixRacer, which I have here in my box somewhere.
You can have my
Where did you buy the cube?
It's also this one. It's also this one.
Where did I get the... Oh, this one, yes. So here's one. That's a PixRacer fully equipped with every possible peripheral, and it's got a drone code, that's called drone code probe. Basically, it's a Blackmagic probe just branded by Zubax. And the nice thing about this particular probe is it's got all of the different possible plugs on it. The one I've got plugged in here is the original Blackmagic probe I got from the original makers in New Zealand many years ago. And I've got that plugged in. It just so happens that I've got that paired with this Pixhawk 2. You can just as easily use this adapter here and plug it into the little cable on the side of a PixRacer. The other thing you can do, and I'll just demonstrate this, if you don't have debug adapters, it is possible to debug virtually any autopilot that ArduPilot controls. Let me just show you how that's done, and I'll just show some photos. So here is a photo of debugging that is a Revo Mini, and I buy these little probes here. I might even have the probes here with me. They're expensive, don't nick them, but they are worth every penny, and it's a lot of pennies, but it's worth it because it basically allows you to clamp onto any pin on the microcontroller. So if you're into hardware debugging, you want to know what's going on the SPI bus, you just stick the little clamps directly on the pins on the SPI bus, and they're fantastic. Philip?
I had to tell you, but that won't work on many boards for a while.
Yeah, some of the surface mount ones, but this generation of boards got this sweet spot where you can, and you can get in there. Fantastic. This particular one, that's the SWD clock pin. That is the VDD 3.3 volt, and that is the I/O pin. I clamp onto that, and then I put it straight into my ST-Link V2 board that I have here. And it goes, you've got these right ribbon cables come with these boards, but you actually only need 4 pins on here, right? The top 2 in the middle and one of the end ones. And in fact, the main one, if you get problems with this and you find it's really unreliable, the most common problem is you don't have VDD linked. It doesn't know the voltage of the board. There's a trick there. If you can't easily get the voltage of the board, just put 3.3 volt on that from your friendly USB serial adapter. Right, because you know it's 3.3 volts, right? You're just telling it, hey, it's 3.3 volts. In that case, you only need 3 pins like this from your microcontroller, okay? Otherwise, this is the Skyrocket debug adapter. They come with nice little debug adapters that their hardware people make, and that gives a nice breakout and things. Just depends on your board. But basically, almost every board in our current generation of hardware, you can do something like this and get onto the pins. And you need ground plus clock and I/O, and that gives you debug. But then it's useful putting it on some of the others sometimes to look what's happening on the bus or UARTs or whatever. Fantastic, those little pins, those little clamps. Okay, back to debugging. What I'm going to do is I've just configured for FMU V3 Shibios. I'm running the GCC version I'm running is GCC ARM90AVI 6207Q2 update. Unfortunately, GDB versions for debugging, it's been a bit of a nightmare. Only very few GDB versions work well with STM32. This particular one is a sweet one that's 90% of the features work, and the remaining ones you can work around the nastiness. By the way, that's Sid nodding a little bit there because Sid taught me a bunch about GDB quite recently. So thank you, Sid. I'm just passing on stuff.
Can we put this sort of stuff in like the actual download for GDB and stuff like that?
Yeah, particular versions. So unfortunately, the version of GCC that comes as that package doesn't build NuttX at the moment. It does build Shibios. Shibios doesn't care. But it means, so I've got a little script where I actually switch. So if I want GC49, I switch there. If I want the latest 6.3, I switch like that very quickly with a little script. This just sets a symlink. All right, so I've built it. I've configured it as FMUv3. I have built ArduCopter and uploaded it to my Pixhawk 2 cube. There it is. Nothing up my sleeve, uploading it. Now I have, while it's uploading, I'll just show you something. I have a GDB in / etc. I have a little Blackmagic probe rules here, which makes it easier because otherwise when you've got multiple Blackmagic probes, this is on Linux, when you've got multiple Blackmagic probes, they all come with different names all the time. There's a little rules thing you can do so that it always comes up with a consistent name and TTYBMP, and it makes two links, one pointing to GDB and the other pointing to the debug UART, right? Useful to know, but you can always work around it. The next thing is you need the GDB init. Now this is supposed to give you an overview of what's possible, then you go and look for the details later. I'm not expecting you to absorb all this. You will need a GDB init, and the main thing that you need to tell it is how does it connect to the board. With this type of probe, what you're using is this target extended pointing at the UART, right? That it's talking to this thing. So in this case, it's using the magic name that I've got here because I've set it up in my rules. If you were using OpenOCD, you would use this one instead. Now, OpenOCD is if you are using your ST-Link V2 board that I've now lost off my table, that one there, the ST-Link V2, if you had that sort of setup, then you would be using OpenOCD. So just know that OpenOCD is out there and it's worth, in case you find it you can't attach via this one. You also have to say various magic things, say, you know, whether you can access memory or not, or arbitrary memory, like device memory, and various breakpoints are useful. Stop if we panic, so that you don't just sit there wondering why it isn't responding, and you know, put a breakpoint. Put a breakpoint on the hard fault handler of Shibios and the halt handler, chsys-halt of Shibios. Really useful. I also like the confirm off, so it doesn't keep asking me, do you want to keep going, do you want this, do you want that? Yeah, I wouldn't have asked you to do it unless I wanted you to do it, so just go ahead and do it. Alright, so now it's loaded. What I'm going to do is I'm going to connect. Now you run arm-none EABI GDB, which is the ELF ARM for these processors GDB version, and you point at the ELF file, which is, in this case, build FMUv3 bin ArduCopter. You run file on it and it says it's a 32-bit ELF binary. That's what you need to give the debugger. That's got the debug symbols in it, and that's why it's so big. Right, there it is, 25 megabytes. We're not going to fit that on the board. That's all the debug symbols. That's why it's big. Okay, so arm-none E80 by GDB, and I run that. That reads the GDB init from the current directory. Make sure you have the GDB in the current directory. Now, you may find, just a little trick, in your home directory you might need something like this depending on your operating system version, auto-load safe path, because by default, GDB tries to be really safe against nasty GDB inits sitting in your current directory, won't let you do all the things you want to do. In your home directory, you've got to put a GDB init that says, trust everything, I'm a developer, right? I know what I'm doing or think I do. So that's what you need, that little thing. When you get stuck and it won't do things, just remember that you need to look up a way of making GDB allowed to use GDB inits in your local directory. All right, we're now connected. And it's currently at line number 502 of STM32DMA.C. As we saw the other day, Shibios spends a lot of its time doing DMA. When we attached the debugger, it was, surprise, surprise, doing DMA. All right, what we're going to do, we're going to put a break on copter : setup, right, which is the initialization code for ArduCopter. We've got a breakpoint sitting there. Now I'm going to tell it to run again. While I'm holding it up, you'll see the lights flashing when the bootloader runs. LEDs are your friends when you're debugging, right? Look at them to understand what they're doing. There we are. We've now done a break. It's stopped at copter setup. The whole CPU is stopped waiting for your command, all right? Now, not everything, the free running timers keep going. They'll start wrapping and things. You do get some funny things with clocks happening. If you have things doing micros and millis and asking for the system time, that gets odd with debugging. So expect some complaints from subsystems that don't like the fact that 3 seconds have passed since the last sample, right? You just live with that as a debugger. It's not a virtual time like it is in CITL. Okay, the first thing I would recommend at this point, you do the magic keystrokes to bring up what's called the TUI, Text User Interface, or you can get GDB integrated into Eclipse or Emacs or whatever. The one I like is the TUI because it's built into GDB. The magic keystroke, you won't remember it, but you know you need to look it up. You know it exists. Control X, A brings up the magic text user interface inside GDB. So now I can walk up and down the code while debugging it. Right? Now you'll notice that the top pane is highlighted, the border. That's because the focus is on the top plane. Now if you're an Emacs user, that's quite familiar. And in Emacs, the keystroke to move the focus to the bottom pane is Control X O, and now I am focused on this bottom pane and I can use history in this bottom pane with my arrow keys. Okay? Flicking between those two becomes quite natural after a while. Alright, so what we're going to do now, I'm just going to show you a couple of little things in here, then I'm going to do something more useful and show a trick with logic analyzers and timing with debuggers. Just so you get an idea of the flavour, the types of things you might want to do with this system. So we're going to go on to the next line, say N for next line. Alright, we can also debug at the assembly level. We could say, you know, layout ASM, and it's now an assembly, or I can do layout source, and I'm back to the source code. Right, so you can see the assembler. You can also do things like info registers to show all the registers, etc. if you're getting down to that level. Alright, so I'm going to go next line, next line. Now so far it's been sensible. What I'm going to do is do next line a few times. I'm going to go next line down to ArduPilot. Now as Randy and many people know, that's where the guts of the initialization of ArduPilot happens. I'm going to do S to step into that rather than over that. So we get into the guts of it. S, step in. I'm now inside the guts of init ArduPilot, and I'm going to step a little bit. Just watch what happens to the cursor, because it's going to go crazy. I just went backwards. You notice I was on line 23, then I was on line 22. And now I'm back on line 22 again, and now I'm on line 23 again. I'm not going backwards. I'm just telling it next line. Now it's done it again, now it's down here, and then suddenly it's down here, delay of 1 second, right? Now, why is it jumping about like that? Has it gone crazy? Is there a bug in the hardware? Right? Why is it jumping about?
It's allocation.
Sorry?
It's allocation.
Not allocation so much as, in other words, optimization. Optimization is the bane of debugging. Right? When you're doing optimization, the compiler is rearranging code. There's all sorts of rules as to what it's allowed to rearrange, and there are barriers that it can't rearrange across, lock mechanisms. It's jumbling it up, and it makes it a nightmare to debug. So what I'll show you is how to stop it doing that, how to make it saner. And what you do is you go into the code and you find lines of code that look like this. So I'm going to go back to the ArduCopter line, ArduCopter system.c, and I'm just going to go, because if we debug the whole of this file, with optimization on, it's going to drive you nuts as you try to work out the logic. So what I tend to do is I put a pragma in, if you can read that. Sorry about the font. I'm not sure if I can make the fonts bigger all that quickly. What I've done is I've put in a line of code. What I'll do is if I go get diff here, you'll be able to see it. Can you read that more easily with a nice big font? Optimize 0 like that. I've added into the code. All right. That says make the rest of this CPP file not optimized. Okay. Now what I'll do is I will rebuild and reload, right? I'll get out of the debugger and I'll reload, and it will recompile just that one file, and it will load that firmware. And now when I put a break in this ArduPilot and step through it, it'll still jump about a little bit, but not nearly as much. Life will be a lot saner. Particularly, you'll be able to see all the variables. It won't have optimized out the variables to be invisible. All right, so let's go into here now and go into copter, init, ArduPilot, and run, and it'll run the bootloader again for 5 seconds, break into it, and there we are. And now, hey, it's actually going logically down through the code, right? You will, however, notice when you use this optimize 0, there's an interesting interaction between Pragma GCC optimize and our functor code. You'll get a weird compilation error if you put that optimize above the functor header or places where you're using functors. All right, I'm hoping to be able to fix that, at some point. But at the moment, you may find you have to take it further down in the file, otherwise you get a weird compilation error. All right, so now we're in the debugger. We can actually go and see what's happening here and see all the printfs, report version, load parameters, etc. Okay, so now we can have a look at variables. We can look at the copter object. In fact, I've got it in uppercase. P for print. Copter.ap, that's that variable that you know so well, Randy. There's all the elements, those flags of copter.ap. And tab completion is terribly useful, right? So you can actually look at all variables starting with A in the copter object and tab complete them. Okay, so for example, there is the arming altitude meters, all right? Now, I'll just show you, there's a lot to learn about GDB, there's a lot of tutorials out there. I want to give you a flavour of what you can do, right, rather than necessarily going through a complete tutorial. But there's a few really essential things that embedded developers need to know about what they can do with debuggers. I'm going to introduce you to A, breakpoints, and B, watch points, all right? Incredibly useful things. So, breakpoints, first of all, you've already seen the simplest breakpoint. What I'm going to do is put a breakpoint in now Leonard's stuff. How about some function in the attitude control, AC attitude control, and what about the, what are we going to do? Get roll, trim radians, get throttle mix, something like that. All right? And let's set reset rate controller iTerms. Was that going to get called regularly when we start up?
Maybe you start. If you want a guaranteed one, I'd go for
the square root controller.
Yeah, that would be
square root controller. Let's put a breakpoint on the square root controller. Now we will continue, and I'm going to actually connect master dev serial by ID USB ArduPilot mav20. So we're connecting into it. We're now connected with mav proxy to this thing. Okay, and it'll suddenly stop when the debugger. We're inside an ArduPilot actually. So yeah, we have to continue there. Let's see, break on AC attitude control and square root controller, and continue. That should boot up now. This should come up, hopefully. There it is coming up, and hopefully it'll stop, and there it is, where I will put the breakpoint. No, we're still continuing.
When at the moment?
Why is that is not breaking at that point? Sometimes you get the problem with the debugger losing the break, but this OpenOCD is so much better. It actually should be at the... Yeah, no, it is waiting. It's just waiting for that. Okay, now we're not going to get that square root controller unless we go into something like loiter, and we try and won't get it to. Oh, we're now in it. There it has. We've now got to the square root controller. So as soon as we tried to enter loiter, we ended up firing off the square root controller, and we can now go through that and we can look at variables. Now, error. If there's the error is 4.99 e to the minus 11. Use p to look at a variable. And there's the correction rate, etc. Now what I'm going to do is show you a watch point. Now what I'll do is, a watch point is a fantastically useful ability in a debugger because it's in hardware, so it's essentially free. You can only have a few of them. What they are is they watch a memory location, and when the memory location changes, the debugger comes in. All right. Now, why that's wonderfully useful is it doesn't slow it down because it's a hardware watch point. It doesn't slow it down while waiting for it. So what I'll do, a simple example, is I'll do, first of all, I'll print a variable. So I'll p of copter.scheduler debug _value. Okay, that's our debug level that we've got, right? Now I'm going to put a watch on that, and it's put a hardware watch point number 5 at copter scheduler debug _value. That's the value of the shed debug variable, all right? And I'm going to delete the breakpoint on the attitude square root controller and now continue, and we're now in mode loiter there. And now what will happen, if I go and change param set shed debug, if I change that to 2, then suddenly we break inside the code that changes that variable. So we're inside GCS param here, right, inside the set float. So that's, the variable is handle param set. So basically that watch point was sitting in the background at the hardware level, and as soon as whatever nasty thing, whatever thing you wanted to see happened at the hardware level, the debugger gets a signal and it takes over. Now it's wonderfully useful when you're looking for a particular condition. All right, great in Citl, great in real hardware. You want to know, you're getting some strange PWM value, all right? You want to know how it's happening. You put a watch point when it happens, the debugger comes in, you get a backtrace.